Refrigeration systems have a wide range of applications in many industries, from chemical plants to utility power plants. In some processes, refrigeration systems are used to cool liquids, gases, and machinery. Refrigeration systems can also be used for air conditioning to make workspaces more comfortable. Understanding the basic principles of refrigeration makes it easier to understand how the individual components of a refrigeration system operate and how they work together in the refrigeration system. Let's start by establishing what we mean by refrigeration. Some people think that refrigeration is a process that produces cold, but that's not exactly correct. Refrigeration is actually a process that removes heat. In simple terms, refrigeration can be defined as a process of cooling by transferring heat out of a substance. In other words, if you want to cool something, you must remove heat from it. Heat is basically energy. When heat is removed from a substance, the temperature of that substance is lowered. To accomplish cooling, refrigeration systems rely on the heat transfer capabilities of certain fluids. The fluids used in refrigeration systems are called refrigerants. The most commonly used refrigerants are able to absorb large amounts of heat at relatively low temperatures. We'll use this illustration to see how this happens. This valve controls the flow of refrigerant through a section of pipe. When the valve is opened, the refrigerant flows through the pipe past a thermometer. As the refrigerant flows out of the valve, its pressure decreases. This drop in pressure also causes the temperature of the refrigerant to drop. As heat transfers to the refrigerant begins to boil or vaporize. The refrigerant then flows past the thermometer and absorbs heat from the thermometer and the area around it. The temperature indicated on the thermometer decreases as the liquid refrigerant flows by, absorbs heat, and becomes a vapor.
In a distillation system, a liquid mixture is separated into two or more components by partially vaporizing the mixture and then separately recovering the vapor and the remaining liquid. We can review the distillation process by examining the layout of the system used as an example in this program. The system is a continuous vacuum distillation system that separates a binary feed mixture, which is a mixture of two components. Here's a simplified flow diagram of the system. The mixture to be distilled is contained in this feed tank. In this system, the feed mixture is pumped from the tank to a preheater, where its temperature is raised close to the boiling point of the lighter component in the mixture. The mixture then flows into the distillation column, where vaporization occurs and the two components of the mixture separate. The heavier, higher boiling component collects at the bottom of the column as a liquid. Part of that liquid is circulated through a reboiler and back into the column.
Refrigeration involves the transfer of heat. So, to understand refrigeration, it's important to understand some of the basic principles of heat and heat transfer. Basically, heat is energy, and heat transfer is energy in transit. Heat transfers naturally from an area or substance at a higher temperature to an area or substance at a lower temperature. If all other conditions remain the same, the greater the temperature difference, the greater the amount of heat that can be transferred. And the smaller the temperature difference, the smaller the amount of heat that can be transferred. In a refrigeration system, heat is transferred from a substance that is being cooled into a refrigerant. The refrigerant carries the heat through the refrigeration system and then transfers the heat to a substance that is able to absorb the heat. When heat transfers to or from a substance, a couple of things may happen. The temperature of the substance may change, and/or the substance may change its state. In general, matter can exist in three states or phases. It can exist as a solid, a liquid, or a gas. When a substance changes its state, the change is called a phase change. What do you think normally happens when phase change occurs? Normally, whenever a phase change occurs, heat transfer takes place. We'll use this beaker of water to demonstrate a phase change and to identify a couple of types of heat transfer. As the water is heated, heat is transferred to the water, and its temperature increases. The heat that is transferred when there is a temperature change is called sensible heat. In other words, sensible heat transfer is heat transfer that can be sensed by thermometers and other instruments as a change in temperature. As we continue to heat the water, its temperature approaches 212 degrees Fahrenheit and bubbles form in the water. When the temperature of the water reaches 212 degrees Fahrenheit, it stops rising and the water boils. Heat transfer is still taking place and a phase change is occurring. The water is turning into steam. The heat that is transferred when temperature does not change, but a phase change occurs, is called latent heat. The heat that's required to completely change a liquid to a vapor at a certain temperature and pressure is referred to as the latent heat of vaporization. The heat that must be removed or rejected to completely change a vapor to a liquid at a certain temperature and pressure is referred to as the latent heat of condensation. When the refrigerant in a refrigeration system receives heat from the substance that's being cooled, it receives the latent heat of vaporization and becomes a vapor. When the refrigerant rejects heat, it gives up the latent heat of condensation and becomes a liquid. The temperature at which a liquid boils isn't related just to the amount of heat that must be added to the liquid. It's also related to the pressure on the liquid. When the water in this beaker is at atmospheric pressure, it boils at 212 degrees Fahrenheit. If the pressure on the water is increased, the water no longer boils at 212 degrees. More heat is needed to increase the temperature of the water until the new higher boiling temperature is reached. If the pressure on the water is reduced, the water starts to boil at a temperature lower than 212 degrees Fahrenheit. Pressure has a similar effect on condensing temperature. When the pressure is increased, steam condenses at a higher temperature, and when the pressure is decreased, steam condenses at a lower temperature. The same effect occurs with the refrigerants in refrigeration systems. When the refrigerant is at a higher pressure, it boils or condenses at a higher temperature. When the pressure of the refrigerant is reduced, it will boil or condense at a lower temperature. The concepts we've been talking about deal with energy and energy transfer. There's a natural law relating to energy that is very important to the operation of a refrigeration system. It's called the law of energy conservation. This law states that energy can neither be created nor destroyed, only altered in form. Basically, this means that if heat is transferred out of something, it has to go somewhere. In a refrigeration system, heat is transferred from the substance that's being cooled into the refrigerant. It is then transferred from the refrigerant to another substance that can receive the heat. These two substances can be called by names that are helpful in identifying what is happening in a refrigeration system. The substance that heat is transferred from is the heat source, and the substance that heat is transferred to is the heat sink. Every refrigeration system has a heat source and a heat sink. For example, refrigeration equipment in this air conditioning system uses a refrigerant to cool an office space. The heat source is the air in the office space that is being cooled. The heat sink is the outside atmosphere, which receives the heat from the air conditioning system. In this topic, we looked at what refrigeration is, and we examined some of the basic concepts of heat transfer that relate to the operation of a refrigeration system. Let's stop here and try some practice questions on this material. If you want to cool something, you must remove heat from it. Heat is basically energy. When heat is removed from a substance, the temperature of that substance is lowered. To accomplish cooling, refrigeration systems rely on the heat transfer capabilities of certain fluids. The fluids used in refrigeration systems are called refrigerants. The most commonly used refrigerants are able to absorb large amounts of heat at relatively low temperatures. The heat that is transferred when there is a temperature change is called sensible heat. In other words, sensible heat transfer is heat transfer that can be sensed by thermometers and other instruments as a change in temperature. The primary purpose of a refrigeration system is to remove heat from a substance. In most cases, removing heat lowers or maintains the temperature of the substance. To lower or maintain the temperature, a refrigeration system must be able to continuously absorb heat and then reject the heat from the system. This is done through several steps in what is called a refrigeration cycle. We can use an illustration to identify the steps in a refrigeration cycle and see how the cycle works. The cycle we'll look at is called a vapor compression refrigeration cycle. A typical vapor compression refrigeration cycle has 4 basic steps. They are heat absorption, energy addition, heat rejection, and expansion. Since the steps repeat, the cycle is a closed system, and it is designed to operate continuously. The cycle uses a fluid known as a refrigerant to transport heat through the system. Let's take a closer look at the 4 steps. The heat absorption causes the refrigerant to change phase from a liquid to a vapor. Also, the vapor receives heat and its temperature increases. So, in this step, the refrigerant changes from a low-temperature liquid to a higher-temperature vapor. In the energy addition step, energy is added to the refrigerant so that it can move through the rest of the refrigeration cycle. In this step, which can also be called the compression step, the refrigerant vapor from the absorption step is compressed. The compression of the refrigerant increases the refrigerant's pressure and temperature. After the energy addition step, the high-pressure, high-temperature vapor goes through the heat rejection or heat removal step. In the heat rejection step, the refrigerant rejects the heat it absorbed in the heat absorption step. In the process, the refrigerant changes from a high-temperature vapor to a low-temperature liquid. In the expansion step, the liquid refrigerant is allowed to expand rapidly. This expansion causes the pressure of the liquid to drop. When the liquid's pressure drops, its temperature also drops. After the expansion step, the refrigerant is a low-pressure, low-temperature liquid. The low-pressure, low-temperature refrigerant is ready for the heat absorption step. The refrigerant again absorbs heat from the heat source and changes to a vapor, and the refrigeration cycle continues. A vapor compression refrigeration cycle is basically a 4-step process in which heat is absorbed from a heat source and transported to a heat sink where it is rejected from the cycle. A refrigerant is used to transport the heat from the heat source to the heat sink. Let's take a look at the components that are typically used to carry out these steps. In a vapor compression refrigeration cycle, the component in which the refrigerant absorbs heat is an evaporator. In the evaporator, the refrigerant evaporates or boils into a vapor. At the same time, the area around the evaporator is cooled. The evaporator draws heat from its immediate surroundings. This heat is transferred to the refrigerant because the temperature of the refrigerant is lower than the temperature of the evaporator's surroundings. To move the refrigerant through the cycle, energy must be added to it. For many refrigeration cycles, a compressor is used to add energy to the refrigerant so that it can move through the cycle. The compressor receives the refrigerant vapor from the evaporator. Energy is added by squeezing or compressing the vapor into a relatively small space. This increases the vapor's pressure and temperature. The component in which the heat is rejected from the cycle is a condenser. In the condenser, the refrigerant vapor is condensed back into a liquid. As the refrigerant flows through the condenser, it gives off heat. What do you think absorbs this heat? In a condenser, a cooling fluid, which is usually air or water, receives heat from the refrigerant. The refrigerant that condenses in the condenser collects in a receiver. The liquid refrigerant is stored there until it flows on to the expansion step of the cycle. The expansion step in this cycle is carried out by a device called an expansion valve. The expansion valve controls the expansion of the refrigerant and its flow to the evaporator. As the refrigerant passes through the expansion valve, it expands rapidly. This causes the pressure of the refrigerant to drop. The drop in pressure also causes the refrigerant's temperature to drop. So the fluid flowing into the evaporator is a low-pressure, low-temperature liquid. The temperature drop caused by the expansion valve creates a larger temperature difference between the refrigerant and the substance being cooled. This allows more heat to be absorbed. Also, at the lower pressure, the boiling temperature of the refrigerant is lowered. This means that the refrigerant is able to vaporize at a low temperature. In industrial facilities, refrigeration systems are often combined with other systems. Let's look at how a refrigeration system may be used in this way. We'll use a secondary cooling system as an example. Secondary cooling systems are used in many process industries. They remove heat from processes and equipment. A refrigeration system, in turn, removes the heat from the secondary cooling system. Secondary cooling systems typically use coolants such as salt solutions, which are called brine or glycol solutions. Both of these types of solutions have freezing points that are lower than the freezing point of water. This allows the secondary cooling system to operate at lower temperatures than systems that use water as a coolant. The system in our example uses a brine solution. The brine flows through the process equipment where it absorbs heat and cools the equipment. A pump is used to create flow through the brine cooling system. The brine is then pumped to a heat exchanger. The heat exchanger in the brine cooling system is the evaporator in the refrigeration system. In the evaporator, the brine acts as the heat source, and its heat is absorbed by the refrigerant. As the refrigerant flows through the evaporator, it changes to a vapor. The refrigerant then flows on through the rest of the refrigeration system. The cooled brine is directed back to the process equipment, and the cycle continues. In this topic, we saw what a vapor compression refrigeration cycle is and how it works. We looked at the components that carry out the functions of this cycle, and we saw how a vapor compression refrigeration system can be used with a secondary cooling system. Let's stop here and try some practice questions on this material. A typical vapor compression refrigeration cycle has 4 basic steps. They are heat absorption, energy addition, heat rejection, and expansion. Since the steps repeat, the cycle is a closed system, and it is designed to operate continuously. The cycle uses a fluid known as a refrigerant to transport heat through the system. To move the refrigerant through the cycle, energy must be added to it. For many refrigeration cycles, a compressor is used to add energy to the refrigerant so that it can move through the cycle. The compressor receives the refrigerant vapor from the evaporator. Energy is added by squeezing or compressing the vapor into a relatively small space. This increases the vapor's pressure and temperature. The brine flows through the process equipment where it absorbs heat and cools the equipment. A pump is used to create flow through the brine cooling system. The brine is then pumped to a heat exchanger. The heat exchanger in the brine cooling system is the evaporator in the refrigeration system. In the evaporator, the brine acts as the heat source, and its heat is absorbed by the refrigerant. As the refrigerant flows through the evaporator, it changes to a vapor. The refrigerant then flows on through the rest of the refrigeration system.